So getting back to the recording, obviously we ran into this error and the last time I was filming, so that's why I stopped the video. And I was playing around with it and I couldn't find anything wrong, so I was really concerned. But then I just opened a new collab, typed it back in, shift entered, and everything was fine. So I'm not really sure what happened there, so we'll just we'll move on. So next thing we need to do is create a variable for water, and we'll do that by saying by typing p equals che dot props, and then like I said, water, so we'll give it the name water. And then we'll shift enter on that. That one's done. So now we're going to create our first dot map, and we'll give it the name C. So we'll type C equals dot map. We'll blank dot map, and now we're going to create variables for all of the givens in the problem that we got. So we'll do that by typing c.mw. This one is for the mass of the water, and that is equal to 1. Next one we're going to do is c.ti. This is for the initial temperature, and that one is equal to 298 Kelvin. Next variable will be the initial pressure, and that is equal to 1 bar, or in this case, because we are using the standard equations, we'll do pascals, so 1 e to the 5 pascals. And then we have our final pressure, which is 2 bar, or 2 e to the 5 pascals, staying in standard. And finally, we'll have the number of moles of water in the vapor phase. So we'll do C dot NWF, and that is equal to 0.3. Now that we have our variables created, we need to find the volume of the container. So I'm going to name it C.VT for the total volume, and that's going to be equal to a range. We're equaling it to a range because we're not 100% sure, so we're going to have to put in a couple guesses, and we'll just guess the values of 0.01, then we'll do 0 as our lowest, and for our high we'll do 0.03. Alright, next we're going to have to do the same thing just for the temperature range value again. So we'll do C.T equals range, and then the guesses for the final we'll do, say, 350. The low we'll do 300, and for the high we'll do 450. Next we're going to solve for the initial volume of the water, and to do this we're going to have to create a variable, and we'll do volume of the water initial, initial, volume of the water initial, and we'll set this equal to C.mw, which is the mass of the water, and it is being divided by P.rhol C.ti for the initial temperature, and it's being divided by this, which is the liquid density. And then finally we have to import the gas constant R, which is 8.314. We'll shift enter on this one. And then we will continue on with the rest of our code. So we're going to create another dot map. This one is going to be R, and another blank dot map. Sorry, just catching up. And now we're going to create a model for a model function that will take in the dictionaries C and R, which we have created. So then in our model, the first thing we're going to need to do in this dot map is to find the vapor pressure of the water. So I'll make the variable r dot pwv, and it can be determined based on the temperature of the system, which is something that you put in the library. So we are going to set it equal to pvap c dot t for our final temperature. And next thing we're going to need to do is find the volume of the vapor phase. So we create the variable r dot vvap for vapor, and this is going to be equal to c dot vt minus c dot vwi, because there is still some liquid that is initially in the system. That's why we have to subtract out the initial water from the final volume. Okay. Next thing that we are going to need to do is find the moles of air in the system, and we'll be using the ideal gas law, which takes into account pressure times volume over R times T. And to do this, we're just going to type out R dot nair, N being the number of moles for air, and we set this equal to C dot PI for the initial pressure, having this being multiplied by the initial vapor pressure, or I'm sorry, the volume of the vapor. And then obviously, like I said, because it's the ideal gas law, it is being divided by R times the initial temperature. And next thing we are going to need to do is create a variable for the moles of water vapor. And this is similar to the last. We'll use the same formula. We're just going to be changing out some of the variables. Some of the variables, like the pressure of water vapor, will be used instead of the initial pressure right here. And then we'll have the final temperature instead of the initial temperature right here. And to do this, we're just going to type out R dot NWV for the moles of the water vapor, like I said before. And then we just set this equal to R dot PWV. This is one of the things we changed for the pressure of the water vapor. And this is being multiplied by same thing as before. And then the R stays the same, but what changes is the temperature. And finally, we are going back to the equations where Dalton's law was in play. So we need to find the final pressure by creating the variable name R dot P and setting it equal to the ideal gas law. So we use the moles of air times R, and then that is also multiplied by C dot T, the temperature, and then that's all divided by the vapor pressure, and what's also added to the vapor pressure is the pressure of the water vapor. So typing out what I just explained, we have R dot nair times R times C dot T dividing by R dot vvap plus R dot PWV. And next, we are just going to create some constraints to store the values. So we are first going to type P underscore const for constraints, just to keep it short so we don't have to type out the full thing. And this is for pressure. That's what the P stands for. And we're just going to, set this equal to C.pf, pf, and R.p. And the next constraint we are going to do is going to be for the moles of water. And this one is going to be set equal to R dot the moles of the water vapor, and then the final mole, the initial moles of the water vapor and the final moles of the water vapor. And then we just need to return this, so we'll type return, and then in brackets the two constraints we just made. And we'll shift enter after that. And it's saying, invalid syntax. Oh, looks like we forgot the colon. Of course I would forget the colon. And then we go and we have that created. So now we are going to use the VSC function, and we're going to create a variable little VSC, little for underscore. We're going to set that equal to the function that we just created by typing uppercase VSC and then C and then the model, obviously. And then finally we do VSC.solve, and after shift enter it should solve for us. And it looks like it's saying there's something wrong. I know it looked like there was something wrong a little earlier with my C function, but I'm not C.map, but I'm not 100% sure why. Back. Everything looks fine. I'm not sure why it isn't giving us This is definitely interesting. Well, let me just stop the recording and see if I can figure it out.